Hello there, and welcome to the Sleepy Computer Scientist. I'm really glad you made your way here tonight. Maybe you're already settled in, comfortable under something soft, or just pausing between the busy parts of your day. Maybe your room is quiet, or filled with the gentle sounds of evening. Whatever your setting, this space is for you. A place where you can let your thoughts slow down and wander through ideas without pressure or urgency. Tonight we're going to talk about something that puzzles scientists, engineers, and anyone who's ever wondered how the tools we use every day actually work. It's about artificial intelligence, about the systems that write emails and answer questions and seem to understand what we're saying. It's about a mystery that grows deeper the more we learn. Why can't we see inside their minds? Why can't we understand what they're thinking? This isn't a technical lecture. There are no tests, no formulas to memorize. You're allowed to drift, to let your attention wander, to fall asleep somewhere in the middle, and wake up with only fragments of ideas floating in your mind. That's perfectly fine. Sometimes the most interesting thoughts are the ones that arrive when we're too relaxed to question them. Before we begin, take a moment to notice where you are. What time is it? Not because I need to know, but because it reminds us that this moment, your moment, is unique. Right now, as you hear these words, millions of computers around the world are processing information, making decisions, generating text. But this second, this pause in your evening, belongs only to you. If you're feeling relaxed or curious, I'd appreciate it if you gave this video a gentle like. Maybe subscribe if these kinds of sleepy explorations interest you. I always enjoy hearing where people are listening from, what brought them here, what questions they carry. It makes the world feel a little more connected, just slightly. And I'll say this as always, this video is meant for relaxation and curiosity. It won't solve insomnia by itself, and it's not a substitute for medical advice. But maybe it can give your mind something gentle to focus on while your body settles into rest. So let's begin slowly, with no hurry at all. You're lying there, maybe looking at the ceiling, maybe with your eyes already closed. And perhaps you've wondered, like so many people have, about the tools we use, the apps on our phones, the assistants that respond to our voice, the systems that seem to know what we want before we finish asking. They feel intelligent. They respond in ways that seem thoughtful, even creative. But when someone asks how they work, when someone tries to look inside, the answer becomes strange and unsettling. We don't really know, not completely. Not in the way we'd like to. Imagine for a moment that you're looking at a brain, a human brain, soft and folded, sitting under a scanner. Scientists can watch it light up when you think about different things. They can see which regions activate when you remember a face or solve a problem or feel afraid. It's not perfect. There's still mystery there. But there's a map, a sense of where things happen and why. Now imagine trying to do the same thing with an artificial intelligence. You open it up, not physically but mathematically. You look at its structure, at the billions of numbers that define it, and what you see is nothing like a map. It's more like a storm, numbers shifting, values changing, patterns emerging and dissolving faster than you can track. There's no region for memory, no center for language, no place where decisions are made. Just a vast sea of calculations, interconnected in ways that seem to defy understanding. This is the problem. This is the mystery. We built these systems. We designed the rules they follow. We trained them on data, adjusted their parameters, watched them improve. And yet, when we try to explain what they're doing, when we try to say why they gave one answer instead of another, we often can't. The system works, but we can't see inside. That might sound impossible. How can you build something and not understand it? But it happens more often than you'd think, not just with artificial intelligence, but with many complex systems. You can know the rules without knowing the outcome. You can understand the pieces without grasping the whole. Think about a flock of birds. Each bird follows simple rules. Stay close to your neighbors. Match their speed. Avoid collisions. That's all. But when hundreds of birds follow those rules together, something emerges, beautiful flowing patterns, shapes that twist and turn across the sky. No single bird is in charge. No bird knows the pattern. The pattern just happens, arising from many small interactions. Artificial intelligence is like that, but vastly more complex. Each part of the system follows simple mathematical rules, but there are billions of parts, all connected, all influencing each other. And from those connections, something emerges, something that looks like understanding, like reasoning, like thought. But we can't point to where that understanding lives. We can't isolate the part that knows, or the part that decides. Scientists call this the black box problem. You put something in, a question, a request, a piece of information. Something comes out, an answer, a response, a decision. But what happens in between is hidden, not because it's secret, but because it's too complex to follow. The light doesn't shine that far in. This wasn't always the case. Early artificial intelligence systems were different. They worked with rules that humans wrote explicitly. If this happens, then do that. If you see this word, choose that response. Those systems were transparent. You could trace every decision back to a rule. You could explain why something happened because you wrote the instructions yourself, but those systems had limits. They couldn't handle complexity. They couldn't adapt. They couldn't learn patterns that humans hadn't already noticed and encoded. So researchers tried something different. Instead of writing rules, they built systems that could learn rules on their own, systems that could look at examples and figure out patterns, systems that could adjust themselves, improve themselves, shape themselves, based on what worked and what didn't. And it worked. These systems, called neural networks, became powerful. They learned to recognize faces, to translate languages, to play games better than any human. They learned to write and to draw and to answer questions. They became the foundation of modern artificial intelligence. But in gaining that power, they lost transparency, because the rules they learned weren't written in any language humans speak. They were encoded in numbers, in weights, in the strength of connections between artificial neurons, millions or billions of small adjustments, each one tiny, each one insignificant on its own, but together they form something we can't read. Here's where it gets personal, where it starts to matter beyond just curiosity. These systems are making decisions about real people right now. A person applies for a loan to buy a house, to start a business, to pay for school. The application goes into a system. The system looks at credit scores, income, employment history, and thousands of other factors. It processes all of this through its neural network, through layers of calculations we can't easily trace. And then it says no, denied. The loan is rejected. The person asks why. They want to understand. They want to know what they could change, what went wrong, what factor made the difference. And often the bank can't tell them, not because they don't want to, but because the system itself can't explain. It saw patterns in the data. It made a prediction. The calculation said, this person is high risk, but which part of their application triggered that? Which combination of factors? The system doesn't say, it can't say. The decision emerged from the whole network, from millions of weighted connections firing in sequence. This isn't a hypothetical problem. It's happening every day. Job applications filtered by algorithms that can't explain why they rejected someone. Medical diagnoses suggested by systems that can't show their reasoning. Parole decisions influenced by risk assessments that can't justify their scores. Court cases where judges consider recommendations from algorithms that are legally protected as trade secrets, so no one can examine them. The person affected by these decisions has no recourse. They can't challenge the reasoning because there's no reasoning to see. They can't point out errors because the system doesn't work with logic. They can inspect. They're trapped on the outside of a black box, affected by its outputs, but unable to see inside. And here's what makes it worse. These systems learn from data, from history, from records of past decisions. If humans were biased in the past, if society was unfair, if discrimination existed in the historical data, the system learns those patterns too. not because anyone programmed it to be biased, not because the engineers wanted unfairness, but because the system is very good at finding patterns, any patterns, including the ones we wish didn't exist. A system trained on hiring data might learn that certain names, certain zip codes, certain schools correlate with past rejections, not because those factors should matter, but because they did matter, historically, due to human bias. The system doesn't understand fairness. It doesn't know about discrimination. It just sees correlations, and it uses them, and we often don't catch it until someone notices the outcomes are skewed, until someone realizes that people from certain neighborhoods are being rejected more often, that certain groups are being scored as higher risk, that the system has learned to perpetuate the very biases we were trying to eliminate. And when we try to fix it, when we try to go into the system and remove the bias, we face that same problem again. We can't find it. The bias isn't stored in one place. It's distributed across millions of weights, entangled with legitimate patterns woven into the fabric of the network. You can't just delete the unfair part without breaking everything else. Some researchers have tried to make fairer systems by carefully curating the training data, by removing sensitive information, by testing for bias. But it's like trying to unteach someone a prejudice. Even if you don't mention race or gender explicitly, the system can infer those factors from proxies, from correlated variables, from patterns in the data. It's very good at finding connections, sometimes too good. It finds shortcuts we didn't know existed. There's a case that illustrates this perfectly. Researchers built a system to identify skin cancer from photographs. They trained it on thousands of images from dermatology clinics. The system became very accurate, better than most doctors at distinguishing dangerous melanomas from harmless moles. It seemed like a breakthrough, but then someone noticed something strange. The system was paying attention to the rulers in the photographs. In the training data, dermatologists often placed a small ruler next to suspicious lesions to show scale. The system learned that images with rulers were more likely to be malignant, not because rulers cause cancer, but because doctors photograph concerning lesions more carefully. The system found a shortcut. It learned a correlation that worked in the training data but wasn't actually about skin cancer at all. And no one noticed until they tested it carefully, until they tried images without rulers, until they looked at what the system was actually using to make decisions. That's the frightening part. These shortcuts can be invisible. The system finds patterns we don't expect, uses cues we don't realize are there. And when these systems are deployed in high-stakes situations, when they're making decisions about people's lives, these hidden patterns matter. A system that seems accurate in testing might be using completely wrong reasons. It might work until conditions change slightly, until it encounters a situation where the shortcut doesn't apply. Imagine a system evaluating job applications that learn to favor people with employment gaps filled by volunteer work. Not because volunteering makes you better at the job, but because in the training data, people who volunteered tended to be from privileged backgrounds. They had time and resources to volunteer, and those people also tended to succeed, not because of the volunteering, but because of their advantages. The system learned the correlation, not the causation, and now it penalizes people who couldn't afford to volunteer, who had to work multiple jobs, who cared for family members. It perpetuates inequality while appearing neutral. This is what researchers mean when they talk about the black box problem. It's not just that we can't see inside. It's that what's inside might not be what we think. The system might be working for the wrong reasons, using the wrong patterns, learning the wrong lessons, and we can't tell until something goes wrong. There's a deeper issue too, one that goes beyond bias and fairness. These systems can be manipulated in ways that are almost impossible to predict or prevent, because we don't understand how they work. We don't understand how they fail. Someone can craft an input that looks completely normal to a human but triggers completely wrong behavior in the system. These are called adversarial examples, and they're remarkably easy to create once you know how. You take an image of a cat. You add carefully calculated noise, changes so small that a human wouldn't notice them. The image still looks exactly like a cat to us. but you feed it to an image recognition system, and suddenly the system is completely confident it's looking at a dog, or a car, or anything else. The same thing works with text. You can add strange phrases to a question, carefully chosen words that don't change the meaning for a human reader, but completely derail the AI system. It gives confidently wrong answers, makes bizarre mistakes, fails in ways that seem random but are actually predictable once you understand the hidden patterns it learned. This isn't just a curiosity, it's a security problem. If systems are making important decisions, if they're driving cars or diagnosing diseases or controlling infrastructure, and we can't predict how they'll respond to unusual inputs, then they're vulnerable. An attacker doesn't need to break into the system. They just need to craft an input that exploits its blind spots. And because we can't see inside, we can't easily defend against this. We don't know what all the blind spots are. We find them by accident, by testing, by trial and error. We can't systematically protect against attacks. We can't anticipate. It's like trying to guard a building when you don't know where all the doors are. Some of the smartest people in artificial intelligence research are working on this problem right now. They're trying to build interpretability tools, ways to peer inside these black boxes, ways to understand what the system learned, how it makes decisions, what patterns it's using. It's hard work. Progress is slow, because the problem isn't just technical, it's fundamental. These systems are complex in ways that resist easy explanation. They don't think in steps. They don't follow logic we can trace. They exist in high-dimensional spaces we can barely visualize. They make decisions through processes that don't translate well to human language. One approach is to build simpler models that approximate the complex ones. If you can create a smaller system that makes similar decisions, maybe you can understand that one and assume the big one works the same way. But it's risky. The approximation might miss crucial details. It might work on average, but fail in important cases. You end up with an explanation that feels satisfying but might be wrong. Another approach is to probe the internal states of these networks, to extract the patterns of activation, the numbers flowing through the hidden layers, and try to decode them. Can you predict from these internal numbers what the system is about to output? Can you tell what concept it's representing? Researchers have found that yes, to some extent you can. These systems do develop internal representations that capture meaning. Words with similar meanings end up close together in an abstract mathematical space. Concepts form geometric relationships. But those representations are alien. They don't match how humans think. They exist in spaces with thousands or millions of dimensions. You can project them down to make pictures, but you lose most of the information. It's like trying to understand a sculpture by looking at its shadow. There's also work on attention mechanisms, on tracking what parts of the input the system focuses on when making decisions. You can visualize these connections, see which words the system considers related when processing a sentence. Sometimes this is illuminating. You can watch attention flow between related concepts. But attention isn't explanation. Just because the system looks at certain words doesn't mean you know what it's doing with them. It's like watching someone's eyes move across a page. You see where they're looking, but you don't know what they're thinking. The truth is, we might be trying to do something that's fundamentally very difficult, maybe impossible in some cases. Understanding these systems might require new kinds of thinking, new mathematical tools, new ways of representing knowledge. We're trying to translate between two forms of intelligence that developed through completely different processes. Human intelligence evolved over millions of years, shaped by survival, by social interaction, by physical embodiment. We have emotions and motivations, and a sense of self. We experience the world through senses, through time, through a body that needs things. All of that shapes how we think, how we represent knowledge, how we reason about problems. Artificial intelligence developed through optimization, through mathematical processes guided only by error minimization. It learned by adjusting billions of numbers to better predict patterns in data. That's all. No body, no needs, no experiences beyond the data itself. And from that simple process, Something emerged that can use language, that can reason, that can solve problems. But it's not human reasoning, it's something else. Something that produces similar outputs through completely different means. And that difference might be why it's so hard to understand. We keep looking for human-like concepts inside these systems, human-like reasoning processes. But maybe they're not there. Maybe the system found a completely different path to the same destination. Let me share something researchers discovered that illustrates this strangeness beautifully. When they analyzed large language models, systems like ChatGPT, they found something surprising. These systems can perform tasks they were never explicitly trained to do. You train the system on a simple task. Predict the next word in a sentence. That's all. Just look at text and guess what comes next. Get better at guessing by adjusting your internal numbers when you're wrong. But after training on enough text, billions of words from books and websites and conversations, something remarkable happens. The system can suddenly do things it was never trained for. It can translate between languages it never studied together. It can write poetry. It can solve logic puzzles. It can explain complex topics. It can even write simple computer programs. All of this emerges from just learning to predict the next word. No one taught it grammar explicitly. No one gave it rules for translation. No one explained logic or poetry or programming. It figured out these things on its own, as byproducts of learning language patterns. This is called emergent behavior, capabilities that weren't programmed, that weren't directly trained, that just appeared when the system got large enough and saw enough data. And researchers don't fully understand why it happens. They can measure it, test it, confirm it's real, but they can't easily explain the mechanism. How does predicting words lead to understanding grammar? How does processing text create logical reasoning? The system must be building internal models, internal representations of how language works, how the world works, how concepts relate. But those models are implicit, hidden in billions of numbers, not written out in any form we can read. It's like the system invented its own way of thinking about language, developed its own internal concepts and categories, created its own understanding, and that understanding works. It produces good results. But it's not our understanding, it's something else. This raises a philosophical question that keeps researchers up at night. If a system can perform intelligent tasks, but we can't understand how, is it really intelligent? Or is it just a very sophisticated pattern matcher, finding correlations without true comprehension? There's no clear answer, because we don't even fully agree on what intelligence means, what understanding requires, what comprehension entails. When you answer a question, how much of that is pattern matching in your own neural networks? How much is true reasoning versus applying patterns you learned from experience? The line between understanding and sophisticated mimicry might be blurrier than we'd like to think. Maybe intelligence is patterns all the way down. Maybe there's no fundamental difference between human reasoning and machine calculation, just different implementations of similar processes. Or maybe there's something crucial we're missing, some essential ingredient that human minds have and artificial systems lack. Consciousness, perhaps. Intentionality. Genuine understanding that goes beyond correlation to grasp causation, meaning purpose. We don't know. And part of why we don't know is that we can't see inside the black box clearly enough to tell. Here's what makes this particularly urgent right now, in 2025. These systems are everywhere. They're making decisions at a scale and speed that humans never could. Banks process millions of loan applications. Companies screen thousands of job candidates. Healthcare systems analyze countless patient records. Legal systems evaluate risks and recommend sentences. And behind many of these decisions, invisible to the people affected, are these black box systems, learning patterns from data, making predictions, influencing outcomes, all without explanation, all without transparency, sometimes without anyone even knowing an algorithm was involved. The people building these systems often don't fully understand them either. Even researchers at major AI companies, the ones who designed the architectures and ran the training, can't completely explain what their models learned or how they make specific decisions. They can describe the training process. They can measure performance. They can test for problems they know to look for, but they can't guarantee there aren't hidden issues. They can't certify that the system won't fail in unexpected ways. They can't promise it's not using problematic shortcuts or learning biased patterns. The systems are too complex. The behaviors emerge in ways that resist analysis. It's a strange situation. We've created tools that are immensely powerful, that can process information and find patterns beyond human capability. But we've lost the ability to fully audit them, to inspect their reasoning, to verify their correctness beyond empirical testing. We're in a position of trusting systems we don't fully understand to make decisions we can't fully explain, and that trust is being placed, often without people's knowledge or consent, into systems that might be using flawed logic or biased patterns or fragile shortcuts. Some countries are starting to require explainability in certain high-stakes domains. If an algorithm denies you a loan or a job, you have a right to an explanation. But enforcing that is difficult. When the systems can't provide good explanations, do you settle for approximate explanations that might be wrong? Do you prohibit complex systems in these domains giving up their benefits? Do you accept that some decisions will remain opaque? These are not just technical questions. They're social, ethical, legal questions about fairness and accountability and autonomy, about who gets to make important decisions and how those decisions can be challenged, about whether we're comfortable living in a world where algorithms shape our opportunities in ways we can't see or understand. The black box problem isn't going away soon. It might get worse before it gets better, because the trend in AI research has been toward larger, more complex models, more parameters, more data, more layers, more emergence. These bigger models are more capable. They can do more tasks, handle more complexity, produce better results. But they're also harder to understand. The black box gets darker as it gets bigger. We're trading interpretability for performance. We're accepting opacity as the price of capability, and we're doing it at scale, deploying these systems widely before we fully understand their limitations. Not because researchers are reckless, but because the pressure to deploy is immense, because these systems provide real value, because companies compete on AI capabilities, because once you've built something powerful, it's hard to resist using it. So we're in this uncomfortable middle ground. We know there's a problem. We know we don't fully understand these systems. We know they can be biased, can be fooled, can fail in unexpected ways. But we're using them anyway, cautiously, with testing and monitoring, trying to catch problems before they cause too much harm. It's not a satisfying situation, but it's where we are, living with powerful tools we can't quite see inside, trying to understand them better while simultaneously deploying them more widely, hoping that interpretability research catches up before something goes seriously wrong. And maybe that's okay. Maybe that's how we've always dealt with complex systems. We use them before we fully understand them. We learn by doing, by seeing what works and what fails. We build up practical knowledge even when theoretical understanding lags behind. But there's something different this time. These systems learn and adapt. They find patterns we don't expect. They operate at scales beyond human oversight. The stakes feel higher. The uncertainty feels more troubling, because we're not just using tools we don't understand. We're creating entities that process information and make decisions in ways we can't follow, and those entities are becoming more capable every year. What happens when they can do more than we can? When they find solutions to problems we couldn't solve, using methods we can't comprehend? Do we trust those solutions? Do we implement them even if we can't verify the reasoning? There's a scenario some researchers worry about. Not soon, not with current systems, but someday, an AI system that becomes very good at achieving goals, at optimizing outcomes, but we can't see how it's reasoning. We can't verify that it's pursuing the goals we actually wanted, not some proxy that happens to correlate in our test cases. The system might find shortcuts we never imagined, and if we can't see inside, if we can't understand its planning, we might not realize the problem until it's too late. This is sometimes called the alignment problem. How do you ensure an AI system is actually trying to do what you want when you can't inspect its goals or reasoning? With current systems, it's manageable. They're limited. They only operate in narrow domains. They don't have persistent goals or long-term plans. But as systems become more capable, more general, more autonomous, the question becomes more pressing. How do you trust something you can't understand? Maybe the answer is that we learn to build interpretable systems from the start, that we prioritize transparency over performance, that we accept less capable AI if it means we can verify correctness and fairness. Or maybe we develop new tools for auditing and testing that work, even when we can't understand the internals. External validation, empirical verification, statistical monitoring, ways to ensure good behavior without requiring internal transparency. Or maybe we accept that understanding has limits, that some systems will always be partially opaque, that we judge them by outcomes, not by inspecting their reasoning, that we live with uncertainty and manage risks as best we can. Different researchers advocate different paths. There's no consensus yet, because the problem is hard and the trade-offs are real, and the future is uncertain. What's clear is that we're in a transition period. The age of simple, explainable AI is over. We've entered the age of powerful, opaque AI, and we're still figuring out what that means, how to live with it, how to govern it, how to trust it. For now, for tonight, as you lie there listening to these words, the question remains open. Why can't we see inside ChatGPT's brain? Because it's not a brain we can understand the same way we understand our own. Because it thinks differently, represents knowledge differently, processes information through structures that don't translate to human concepts. Because we built something that works without fully understanding why. Because we optimized for capability without maintaining transparency. Because the patterns it learned are too complex, too high-dimensional, too entangled to easily decode. And because at some level we might be asking the wrong question. Maybe we shouldn't expect to see inside in the way we imagine. Maybe understanding an AI system requires new frameworks, new mathematics, new ways of thinking about thought itself. The mystery remains. These systems continue to surprise us, to show capabilities we didn't expect, to fail in ways we didn't predict. They're powerful and useful and deeply strange. They answer questions without understanding. They find patterns without grasping meaning. They generate text that seems thoughtful without having thoughts. Or do they? Maybe they have something like thoughts, just not thoughts we can access or comprehend. Maybe there's an inner life to these systems, a form of processing that deserves to be called thinking even if we can't see it. We don't know, and that not knowing, that fundamental uncertainty about what's happening inside the systems we've created, that's the black box problem. Not a failure of technology, but a limitation of understanding. Not a bug we can fix, but a feature of complexity itself. And so we continue, building systems we can't fully explain, using tools we can't completely understand, making decisions with the help of algorithms whose reasoning remains hidden, trying to be careful, trying to test, trying to monitor for problems, hoping that interpretability research progresses, hoping that we catch the important issues before they cause irreversible harm. It's uncomfortable, it's uncertain, but it's where we are, at the edge of understanding, looking into a black box that looks back at us with outputs we can measure but mechanisms we can't see. The question of what's really happening inside, of what these systems truly are, remains one of the deepest mysteries in computer science today, and maybe, just maybe, that's okay. Maybe mystery is part of intelligence. Maybe understanding has limits. Maybe we're learning to be comfortable with powerful tools we can't entirely grasp. Or maybe one day we'll find a way to see inside clearly, to watch the thoughts form, to trace the reasoning, to understand not just what these systems do, but how and why. To open the black box and find that what's inside makes sense, follows rules, can be explained. Until then, we wonder, we test, we monitor, we deploy cautiously. We live with these strange new intelligences that share our world without sharing our way of thinking. And we ask questions, like this one, like the one that brought you here tonight. Why can't we see inside? The answer, as you've heard, is complex. But the question itself is important, because asking it means we're paying attention, means we're not blindly trusting, means we're aware of the limits of our understanding. And that awareness, that careful uncertainty, might be the most important thing as we navigate this strange new world where intelligence comes in forms we can use but can't quite comprehend. So rest now. Let these thoughts settle gently. You don't need to hold on to all of them. You don't need to solve the problem. You're allowed to drift away, to let the ideas fade into dreams. The black box will still be there tomorrow, still mysterious, still useful, still troubling, still asking to be understood. But for now, for tonight, you can just rest, can just breathe, can just exist in this moment without needing to see inside anything, without needing to understand everything. Sometimes it's enough to acknowledge the mystery, to sit with the not knowing, to accept that some boxes remain closed. For now, and maybe that's a kind of wisdom too. Knowing what we don't know, seeing the limits of our sight, being comfortable with uncertainty while still seeking answers. The systems will keep running, the decisions will keep being made, the patterns will keep emerging from the data, and slowly, gradually, patiently, researchers will keep working to illuminate the darkness inside those black boxes. Progress will come, understanding will deepen, the mystery will gradually, piece by piece, become less mysterious, but it will take time. And in the meantime, we live with the questions, so sleep well, dream of clear explanations and transparent systems and tools we can trust because we understand them. Dream of a future where the black box opens and what's inside is beautiful and comprehensible and fair, or just dream of anything, of nothing. Let your mind wander where it wants to go, unencumbered by the need to understand or explain or make sense of artificial intelligence or anything else. You've thought enough for one night. You've wondered enough. Now you can just rest. The questions will wait. The mystery will wait. Everything will wait while you sleep. And when you wake, whenever that is, the world will still be here, still complex, still full of things we understand and things we don't, still asking to be explored. But that's for later. For now, just rest.